Hello everyone, good evening. Friday, 8 o'clock. We're all enthusiastic to learn thermodynamics and enthusiastic to support your learning. I would like to thank Ekeeda for creating this platform to reach you. Ekeeda is a trustworthy organization. It is striving hard to make the learning simple. I request all of you to buy Ekeeda videos and that will support Ekeeda to make the learning more simple and to reach also more students. And it is my good luck to have association with Ekeeda. I once again would like to thank Ekeeda for creating this platform to reach all of you. Okay, in this live session, I would like to discuss Carnot engine and also derive expression for efficiency of Carnot engine, and I will solve a few problems on second law of thermodynamics. I request all of you to have a more interactive session. I expect more and more questions. I try to solve your queries. Okay. Any sound issues, please let me know. Okay, this Carnot engine will have 4 processes, out of which 2 are reversible adiabatic process and 2 are reversible isothermal process. To derive the expression for efficiency of a Carnot engine, we will have these following assumptions that there is no friction between the piston and the cylinder. It is assumed that while movement of the piston, there will not be any friction between the piston and cylinder. The second one is the walls of the piston and cylinder are perfectly insulated. That means there is no heat interaction through those walls of the cylinder and piston. The cylinder head is so arranged that it can be perfect insulator or a perfect conductor as well. That means during isothermal process, a perfect conductor is placed to have a heat interaction. During adiabatic process, insulator is placed. A source and sink with infinite quantity of heat at high and low temperature respectively. So there will be a heat source that will have infinite quantity of heat at a high temperature, and also it will have a sink that will have infinite quantity of heat at low temperature. A perfect gas is used as a working medium. Here a working medium is a perfect gas. So let us have the pressure volume diagram of this Carnot engine cycle. Here process 1 to 2 is isothermal compression. It is a reversible isothermal compression, and then process 2 to 3 is reversible adiabatic compression, and process 3 to 4 is reversible isothermal expansion, and process 4 to 1 is reversible adiabatic expansion. Here heat is added during the isothermal process 3 to 4, which is at a higher temperature, that is actually T max, and heat is rejected from the system in the process 1 to 2 at a temperature T minimum, and the same thing is plotted on temperature entropy diagram. Yeah, sure. I am going to solve problems. Okay. This is when it is plotted on temperature entropy. Okay, some students are telling sound disturbance is there. Let me check. Okay, I will try to resolve that issue. When it is plotted on a temperature entropy plot, the process 1 to 2 is isothermal process. Here temperature is constant. And process 2 to 3 is adiabatic process. Here there will not be any heat interaction. That is also called as constant entropy process. It is isentropic process. And process 3 to 4 is once again isothermal process, reversible isothermal process, during which heat is added, and during the process 4 to 1 it is adiabatic expansion. Once again there is no heat interaction during that, and heat is rejected from the working substance in the process 1 to 2, that is reversible isothermal process. Okay, after this let us discuss okay, I'll continue in 2 minutes. Okay, I'm trying to resolve that sound disturbance if it is there. Okay, let me check. Okay. Let us discuss these processes one by one. The first one is process 1 to 2. It is isothermal compression process. I will have expressions also with that. Process 1 to 2 is isothermal compression. Isothermal compression. It is reversible isothermal compression. Okay, the first process 1 to 2 is reversible isothermal compression. So during this process, that is process 1 to 2, the cylinder head is replaced by conductor, and above that conductor heat sink is placed. When the piston moves from the outer dead center towards inner dead center, it compresses the working substance air, and the compression of the air will increase the temperature of the air. But here the process is isothermal process. The temperature has to be maintained at a constant. Temperature should not be changed. To have the constant temperature process, that equivalent amount of heat must be rejected. For that reason, heat sink is placed along with conductor at the cylinder head, so that heat rejection takes place, and this process should take place very slowly to maintain the constant temperature. And the process 1 to 2 will have a compressive work, and that work is given by W1 to 2 is equal to Q out. So whatever that work that is supplied, that will be converted into heat, and that is rejected to the heat sink. So W1 to 2 is equal to Q out, that is equal to isothermal work done, that is given by P1 V1 into ln V2 by V1. It is final volume divided by initial volume. And for this P1 V1, we can write it as RT1, PV equal to RT. For ideal gas, we have the equation PV equal to RT. So for P1 V1, we will have R into T at 1, T at 1. This is T at 1. This is T minimum, right? So R into T minimum into ln V2 by V1. After further simplification, I will write it as minus R T minimum into ln V1 by V2. So if I change the numerator and denominator, the symbol will be negative. So it is very basic ln simplification, I can say. So this is the process 1 to 2. It is isothermal compression, during which heat is rejected to the heat sink. And then the next is process 2 to 3. The process 2 to 3 is adiabatic compression, during which no heat interaction takes place. So let's see what happens in the process 2 to 3. Process 2 to 3 is reversible adiabatic compression. During this process, the cylinder head is replaced by an insulator, because it's an adiabatic process, there will not be any heat interaction during that. So obviously when it is compressed, its temperature increases. Here it is shown in this plot, its temperature increases from this point to this point, it is 2 to 3. So that will be increased from T minimum to this T max, this T maximum. So this process should take place as fast as possible to avoid the heat loss to the surroundings. Then the work done during this process 2 to 3, that is work is done on the system and work interaction. So that is W2 to 3 is equal to P2 V2 minus P3 V3, it is divided by gamma minus 1. So this is the work done expression for adiabatic process. Then for this we can simplify in terms of R and D. So here P2 V2 is R into T at 2. See, this is T at 2. T at 2 is this T minimum. So it is R into T minimum minus for this P3 V3 R into T at 3. T at 3 is T max. So I'll write down that one. R into T max divided by gamma minus 1. So here I will take R common factor. So this will be R into T minimum minus T max divided by gamma minus 1. If I write down in this term in this way, this will be minus R into T max minus T minimum divided by gamma minus 1. It is minus R into T max minus T minimum divided by gamma minus 1. So this is for adiabatic compression, that is process 2 to 3. And then for this process 3 to 4, it is isothermal expansion. For that, let's write down this one first, and then let's write down the equation for that work interaction. So here process 2 to 3. Process 2 to 3, it is process 3 to 4. It is isothermal expansion. So during this isothermal expansion, the cylinder head is replaced by a conductor because heat has to be transferred, and then a heat source is placed. The reason why heat source is placed means because during this process gas will be expanded. When gas expands, its temperature decreases. But here it is an isothermal expansion, so to have the constant temperature, equivalent amount of heat must be added to the working substance, that is gas. So heat source is brought to the cylinder head, and then the work involved, that is expansion work, that is equal to heat that is supplied during that process, and that can be written as W three to 4 is equal to, it is P3 V3 into ln V4 by V3. Then this P3 V3 can be written as R into T at 3. So R into T at 3. T at 3 is T max. So let us write down this as R into T max V4 by V3. So this is the work involved during this process 3 to 4, and that is equal to heat that is supplied during this process. Okay, I am continuously telling that there is some sound issue. No, Mr. Pranay, I don't have any electric device here. If you permit me, I will restart the system. No, there is no earphone here. There is no earphone also. Okay. Okay, all of you please wait for a while. I will have my system. Yes. Yes. Okay. I will try this. Okay, I hope the problem is resolved now. If the problem still persists, please let me know. I hope the problem is resolved now. Okay, that's fine. Okay, dear students, if you have any questions, please post me so that I will answer those questions. So this is isothermal expansion. During that, heat will be added to the gas. So then the heat addition during that process is W3 to 4, that is equal to P3 V3 into ln V4 by V3, that is equal to R into T max into ln V4 by V3, that is actually equal to Q1. Then the next process is process 4 to 1. The process 4 to 1 is adiabatic expansion. Okay, the process 4 to 1 is adiabatic expansion. Once again, during this process, the cylinder head will be having the insulator, so that there will not be any heat interaction. So during this expansion, its temperature decreases from T maximum to T minimum, and we will have that expansion work, that is W from 4 to 1 is equal to P4 V4 minus P1 V1 divided by gamma minus 1, that is equal to, here P4 V4 is R into T at 4. So what is T at 4? T at 4 is T max, that is here it is T max minus R into T at 1 is as you already know, it is T minimum, that is divided by gamma minus 1. So then this can be written as R into T max minus T minimum, this is divided by gamma minus 1. So now let us have the net work done during this process. So that net work done is given by W net is equal to W from 1 to 2 plus W in the process 2 to 3 plus W in the process 3 to 4 plus W from 4 to 1. Now W 1 to 2 as it has already been discussed here, W 1 to 2 is R into minus R into T minimum into ln V1 by V2. So it is minus R T minimum into ln V1 by V2, and then process 2 to 3 we have W 2 to 3, that is given by minus R into T max minus T minimum divided by gamma minus 1. So this is minus R into T minimum, so not T minimum, minus R into T max minus T minimum divided by gamma minus 1 plus W 3 to 4 is given by this R into T max into ln V4 by V3. So this is R into T max into ln V4 by V3, then W 4 to 1 is given by this one R into T max minus T minimum divided by gamma minus 1. So that is equal to R into T max minus T minimum, that whole divided by gamma minus 1. Here we have adiabatic expansion and adiabatic compression, which are W4 to 1 and W2 to 3 respectively, and they get cancelled. See, these two terms get cancelled. One has minus and the other one has plus symbol, so that can be cancelled. Then this is equal to R into T max into ln V4 by V3 minus R into T minimum into ln V1 by V2. See, this is the net work done during the cycle, that is Carnot cycle. And then next for adiabatic processes 2 to 3 and 4 to 1, we can have a temperature and volume relation like this for the process 2 to 3. Process 2 to 3 is adiabatic compression. Here temperature and volume are related by this one, that is T2 V2 to the power gamma minus 1 is equal to T3 into V3 to the power gamma minus 1, and this can be written as T3 divided by T2 is equal to V2 by V3 whole to the power gamma minus 1, and that can be written as T at 3 is T max, T at 2 is T minimum, so that we can have T3 as T max divided by T at 2 is T minimum, that is equal to V2 by V3 whole to the power gamma minus 1. So this is equal to V2 by V3 equal to T max divided by T minimum whole to the power 1 by gamma minus 1. This is for adiabatic compression. Similarly for adiabatic expansion, that is process 4 to 1. For process 4 to 1, the temperature and volume are the entropy is constant. During that it is an isentropic process. Entropy is constant. Process 2 to 3. All adiabatic processes are isentropic process. So there is no change in entropy during these processes, which are process 2 to 3 and process 4 to 1. Then process 4 to 1, temperature and volume are related in this way, that is T4 V4 to the power gamma minus 1 is equal to T1 V1 to the power gamma minus 1. So that is equal to, I'll write down like this, T4 by T1 is equal to V1 by V4 whole to the power gamma minus 1, and this can be written as T at 4, as you have already seen, it is T max, and T at 1 is T minimum. So it is T max divided by T minimum is equal to V1 by V4 whole to the power gamma minus 1, and this is equal to V1 by V4 is equal to T max divided by T minimum whole to the power 1 by gamma minus 1. And in these two expressions you are seeing here, if you compare these two, right hand side terms are same, so that we can write like this, that is V2 by V3 is equal to V1 by V4. If I rearrange this, if I bring this V4 to this side and V2 back this side, this becomes V1 by V2 is equal to V4 by V3. So the ratio of compression and expansion are like this, that is V1 by V2 is equal to V4 by V3. Now let us have efficiency. That efficiency is given by, it is more popularly known as it is net work done divided by heat, that is input. Here we know net work done, we derived here W net equal to RT max into ln V4 by V3 minus RT minimum into ln V1 by V2. So W net, as it has already been done, it is R into T max into ln V4 by V3 minus R into T minimum into ln V1 by V2. This whole thing is divided by Q in. That Q in is equal to work done, that is during the process 3 to 4. This is Q in, so it is RT max into ln V4 by V3. So here we can write down it as R into T max into ln V4 by V3, and this we can rearrange. Here the term R is common. I will take R as common factor, and then here we have ln V4 by V3 is equal to V1 by V2. That is what exactly shown in the previous step, so that we can take ln V4 by V3 common factor. So it is ln V4 by V3, R into ln V4 by V3 into T max minus T minimum, this whole divided by R into T max into ln V4 by V3. So here this R and R get cancelled. Ln V4 by V3, ln V4 by V3 get cancelled. Then we will have the expression in the next step that is equal to T max minus T minimum divided by T max. Let us take T max as T1, T max as T1, T minimum as T2. Then the expression becomes like this, equal to T max is T1 minus T minimum is T2 divided by, once again, T max is T1. So this can be simplified as 1 minus T2 divided by, so this is the efficiency of Carnot engine that has all the four processes reversible. This is a reversible heat engine that will produce maximum efficiency, and the efficiency we can write down also in this way, that is efficiency equal to W net divided by Q in. So W net will be written as Q in minus Q out divided by Q in. So let us take temperature that is entering the system as Q1 minus Q out as Q2 divided by Q1. So this will be 1 minus Q2 divided by Q1. So this is the efficiency expression for Carnot engine in terms of heat transfer Q1 and Q2. Here Q1 is heat entering and Q2 is heat rejected. Now both the expressions are efficiency. Their left hand side are same, that is eta. So it is 1 minus Q2 by Q1 is equal to 1 minus T2 by T1. So here the 1 and 1 get cancelled, and this minus 1 and minus 1 in the left and right side they get cancelled. Finally we will have the ratio like this. It is Q2 by Q1 is equal to T2 by T1, or this can also be written as Q1 by T1 is equal to Q2 by T2. So this is how temperature and heat transfer are related in case of this Carnot engine, and this is the derivation of Carnot engine, the derivation of efficiency of Carnot heat engine. If any questions are there regarding this, questions are welcome, and I will continue with the problems after this one. I am taking this problem. Before going to that problem, I would like to expect few questions if you have any questions. Okay, I will be moving this with this problem. If you have any questions, I will resolve while solving this problem. The minimum power required to drive a heat pump which maintains a house at 20 degrees Celsius is 3 kilowatt. If the outside temperature is 3 degrees Celsius, estimate the amount of heat which the house loses per minute. That is very important. What is the minimum, what is the heat that is lost from the room per minute is the question. So here let us start this problem with block diagram. See, for this we have a heat pump. The minimum power required, that means it is a reversible heat pump because it requires a minimum power. So let us start with block diagram. For that, the very first I will have a heat pump. So This heat pump receives W HP amount of work, and this will pump the heat to a house which is maintained at 20 degrees Celsius. Let us take it as T1 dash. So T1 dash is 20 degrees Celsius. So, and outside temperature is 3 degrees Celsius. So let us take T2 dash as 3 degrees Celsius. So this heat pump receives Q2 dash amount of heat from the sink or atmosphere, and pumps Q1 dash amount of heat to the room which is maintained at a temperature of 20 degrees Celsius. Here we should find out the amount of heat which the house loses per minute. The purpose of heat pump is to maintain the room temperature higher than the atmosphere temperature. For that we should supply the heat to the room that must be equal to the heat that is lost from the room during that process. So here Q1 dash will be equal to the heat that is lost from the room to have the temperature at 20 degrees Celsius. So if we find out Q1 dash, that is the same as the amount of heat that house loses per minute or whatever that. So for that we have the work, that is power, that is input. W input, that is W of heat pump, is given as kilo